Session given by Sergei Rogosin from Belarusian, and we will speak about factorization of triangular functions, arbitrary orders. Please.
Thank you. I would like to say many thanks to Professor Mishuris personally, to Anastasia, and of course to David Abrahams for giving me a possibility to speak here. When I think about my talk and observe the lectures which are given here, I change my mind and suppose to speak about very simple things from the very beginning of factorization in a part from the very beginning. But anyway, very old-fashioned things which can be, I suppose, can be interesting for those who is working nearby to factorization theory. I would like to say that this work, the part which is pure machinery, is done due to collaboration with Professor Mishuris, my former dean, Professor Primachuk, and my wife, M.Dubatovskaya. I will speak about tight connection between factorization problem and Riemann boundary value problem. Please excuse me for using title Riemann boundary value problem, because sometimes I will turn to the so-called Riemann-Hilbert problem, which is in another nature, and not to mix these two problems, I use the name Riemann boundary value problem, which is presented on this slide. This is problem 1. Problem 1 is factorization problem. Factorization problem is representing of a function given on the certain curve in the form 1 with diagonal matrix as here, and factors which are described, maybe better described here on this blackboard. The factors, when I speak about factorization of the matrix which is continuous, or even better, Hoelder continuous, then in this case I suppose that factors should be analytic and continued as an element of Hoelder space on the boundary. Not only function g plus g minus, but also their inverse. This is a standard classical formulation of factorization problem, and as I have said, this problem is tightly related to the problem of so-called Riemann boundary value problem. The story which I have to speak about is on connection between these problems. Some formulas are written here. It is well known, if we have a good class of matrices, then we can either solve boundary value problem or solve factorization problem. These are quite close friends. You see again some machinery here. If, for instance, we have a factorization, then we put factorization into the boundary condition and obtain relation which is already scalar. This relation which is already scalar, and the only question is to consider the behavior of the elements on the infinity. This is all. If we are lucky that these powers are positive, then we have many solutions. If not, we have no solution in the prescribed class. The class of solution for boundary value problem is exactly the same as a class of factors in factorization problem. Vice versa. Vice versa means many of you read the fundamental book by Mushilishvili, and in this book it is written definition of canonical matrix related to boundary value problem. This definition means that a matrix should satisfy the boundary condition, should satisfy this relation. Now these are vectors here in one, but here he plus, he minus are matrices. They should satisfy boundary condition, and canonic means the following, that the sum of orders of columns should be equal to index of determinant of matrix G or winding number, as it was said several times today or yesterday. In this case, when we are lucky to find canonical matrix, then we arrive to factorization in this form, and here these are k, j are equal to orders of columns. Order of column means the minimal order of elements of the of this column, and these are k, j are simply partial indices. This is a story about relation of between these two problems. Of course, we know that in spite of this approach, this is already approach. If you wish to factorize something, you can solve a boundary value problem. You can construct canonical matrix and obtain solution in the corresponding form, again by examining the behavior at infinity. At infinity, why at infinity? Because usually in classical formulation, the boundary curve is a finite curve, for instance, Lipschitz curve, and in this case, and we suppose that 0 is inside the curve and infinity, of course, is outside. If we change mind a little bit, for instance, if we work in some problem related to Wiener-Hopf equation, we use gamma being real line. In this case, all the same, but diagonal matrix which appeared in factorization has this form. It means simply that we turn infinity into the point I. And what we have about examination of behavior at infinity in the case of finite curve, then in this case we should examine the behavior at the point I. Okay, maybe it is good to go further. A few years ago, we start with Gennady the work on factorization, and in particular, we published this survey on constructive methods of factorization of matrix function. And what was our purpose? to examine the most popular approaches which are working in constructive way, which allow us either to get either exact formulas or some kind of approximate formulas to get partial indices, which partial indices which are here, or where is it? No. Okay, to find partial indices and construct analytic matrices G plus and G minus, which are called factors. Furthermore, we do something with approximate methods and publish two papers in three papers. They published 3 papers concerning approximate procedures for constructing solution of factorization problem. They can be found easily. What I would like to say now, it is a little bit strange for a report at such a conference which get together people related to Wiener-Hopf and so related to factorization problem. Anyway, I would like to ask your excuse. I present here a number of general results in factorization which are known up to now. These are results. In fact, some of these results were discussed before. For instance, just in the morning, Ilya said about non-singularity, which is at least necessary condition for many cases, but in the case, in the classical case, when we have a good matrices, say Hoelder continuous, for instance, this is not only necessary but also sufficient condition for factorizability. Next result is also well known, and this is already in fashion all the time to say that partial indices can be taken in a certain order. It is not a big procedure, but anyway, we can always suppose that partial indices are ordered in this sense. Ordered in this sense. Next is also folklore result. I found this result in the paper by Gachov in 1950, but probably it is known even before. The result is that the sum of partial indices is equal to index of a determinant of a matrix. Next, there is a very big and strange obstacle in the study of factorization problem. This obstacle is stability. Stability, at least 2 competitive results appeared in 1958. These are the big and seminal paper by Kochberg and Crane, and also the paper by Bogdan Boyarsky in the same year. Stability means that we can sometimes approximate and organized approximate procedure, but if we ask approximate in the whole class of considered matrices, then it is not always possible. a necessary and sufficient condition is this one. This is for 2 by 2 matrices, but anyway, the biggest partial index minus smallest partial index should be not greater than 1. So we have either all equals or only 2 collection of indices with difference equal to 1. All 2 and the rest 1, all 100, the rest 99, and so on. This is discussed in a wide contents in the paper by Goldberg and Krupnik. And in particular, the classical example was given when we perturb matrix only in one element, in very small number. It can appear that after refactorization, the matrix will have another set of partial indices. It is well known. So in non-stable case, factorization non-stable in a sense that the partial indices can be changed. That is why it is really obstacle for numerics. If people start to approximate or calculate numerically the factors and partial indices, they should be careful about the situation. If the situation is not so good, if the situation is not stable, then we can arrive at a problem. These are problems cannot be seen from the numerical procedure. But finally, we will get another type of factorization. What next? Here I mentioned several papers by people about this stability, and I would like to say that there are several examples which show that stability really gives some obstacle for our procedure.
Sorry, Sergei, these two first references, 53, 54, who is this?
Shmulyan. This is Shmulyan. Another general result, I also found this result in a known paper by Torsten Erhardt and Ilyas Petkovsky. This result is very simple, showing that we can say that partial indices for a given matrix are determined uniquely, but not factors. What are relations between factors for different type of factorization? It is proposed, for instance, in this paper I mentioned here in 2001. Next, this result I've said about just a few minutes ago. Theoretically, this result was proven already by Goldberg and Crane, but in the Ilya paper and Ilya and Torsten paper, it was given a procedure how to determine the factors in the case when we have two different factorization. Special case, of course, n equal to 1. In n equal to 1, situation is quite the same, but even better, because we know the result in advance. this result, in the case of a given Hoelder continuous matrix, is presented solution of boundary value problem 1, in terms of Cauchy type integral. Properties of Cauchy type integral are well known, and I will speak a little bit about this few minutes later. What is case n equal to 1, and what we lose when we go further for large number m. Next result is also well known about factorizability. Very funny result is by Markus and Matsayev. I always, when I speak about factorization, I always mention this result. The result is very interesting. If 2 by 2 positive and Hoelder continuous matrix possess factorization, then if all 2 by 2 positive and Hoelder continuous matrix on a given curve possess factorization, then this contour should be circle. Funny result.
If it is a conformal net that is smooth.
No. This is very interesting result. The question is that all matrices, all positive and Hoelder continuous matrices possess factorization. Sorry, I forgot the word. Canonical factorization. Canonical factorization means all partial indices are equal to 0. When I read for the first time this result, for me was also very surprised. But anyway, it was proved that it is so. It is so. Next negative result, already said by Ilya today, that for simply continuous matrix, it is not always possible to get factorization. So we either need to understand it in another context of functional spaces, or give some extra condition on matrix, but for simply continuous matrix it is not always possible. And finally, I would like to say that in fact there are two possible factorization: right factorization and left factorization. This one is left factorization, and right factorization vice versa, beginning from minus lambda and then plus. In fact, both collection of partial indices do not necessarily coincide, but their sum is always the same, of course, because of the result I already mentioned. And besides, there is a very funny result by Feldman and Marcos. The result is the following: if we have two collection of numbers satisfying this condition, then we can find a matrix which have left indices from the first collection as a first collection and right indices as a second collection. So this is also very surprised result. Maybe I can stop here before starting some technical things and return to the history to the history. For me, it was interesting to understand when the factorization problem as a special problem, special mathematical problem appear. And in fact, from my feeling, this story is a little bit in shadow. In fact, as I have said, I speak about the problem 1 as a Riemann boundary value problem. Really, Riemann formulate a kind of problem which can be understood as a boundary value problem in the sense written here. But in fact, Riemann formulate completely other problem. Riemann formulates the problem related to construction of complex differential equation with a prescribed property which was later called monodromy, the monodromy, preserving monodromy. Later on, Hilbert returned to this problem and consider it as an important one, even put it into the list of his problem for 20th century as a 21st problem. This 21st problem is formulated as to construct differential equation of Fuchsian type, complex differential equation of Fuchsian type with a given monodromy. This problem was attacked by many mathematicians, not only because of relation to the list of to the list which was made by Hilbert, but also from a different point of view. This is very interesting, as from theoretical as from practical point of view. And in 1908, it was presented 2 papers by Plemelli, who said that he solved the problem, this Riemann-Hilbert problem, and in fact, more than 20 years it was supposed that it is really correct. More than 80 years. What is important to say about this situation? What is important to say about Plemelli work? It is important that, in fact, in the work of Plemelli, the machinery was the following. He reduced the above said Riemann-Hilbert problem of construction of complex differential equation to the solution of a system of Fredholm equation by using properties of Cauchy type integral. That is why we know that formulas for boundary values of Cauchy type integral is called Sahotsky-Plemelli or simply Plemelli formulas. By using this property, he reduced the problem to the solution of the system of Fredholm equation. By the way, what was introduced by Plemelli, what is interesting from the context of my today talk, the Plemelli was the first who introduced the property of canonical matrix. In exactly this sense, canonical matrix was discovered by Plemelli. Plemelli found that by using canonical matrix, he can work with his procedure. So it seems Plemelli could formulate the factorization problem as itself, as it is now known for us. Since it was recognized that Plemeli result is complete, at least for that time, then people turn to some other situation related to this problem, to the Riemann-Hilbert problem, and we know several results of constructive type. Construction, special classes of singularities, special classes of monodromy matrices. It was studied by several mathematicians. I write here the papers by Roehl, Danilevsky, and Yerugin, and many other people. For instance, in the paper by Yerugin, and by the way, Yerugin wrote the big book which was called Riemann problem, simply. It means Riemann-Hilbert problem. And in this book he found many relation of this problem to other problem of mathematics. For instance, he discovered that so-called Penlevé complex differential equation are related to the solution of the Riemann-Hilbert problem, and Penlevé equation is known for long-lasting theoretical study, as well as for several applications. So it should be said about this. What next? What next? Where, in fact, the interest to the Riemann problem rediscovered, and when people start to study the problem in the form I wrote there. By the way, a starting point was not scalar problem. Starting point was, in fact, again matrix problem, vector matrix problem. So the problem 1 with matrix coefficient. With, it is because of interest to this. It was because of interest to Riemann-Hilbert problem. Returning to the scalar case, we can say the following. We can say about the following very simple formula, which is written here. In the case when our scalar case, when our matrix G is Hoelder continuous, non-vanishing on the contour, then we can introduce the integral of this type, and this integral gives us a solution of our boundary value problem. It was maybe for the first time it was discussed in the paper by Gachov in 1950. What's happened if we simply write this integral for the matrix? Instead of function here, we wrote matrix. Is it possible to calculate logarithm of the matrix? Yes, of course. The same as for any other analytic formula, we can exploit the series and obtain logarithm of the matrix. But where is the problem? Where the problem can appear? The problem appear in very simple. You see, this is what's happened if we have simply scalar case. In the scalar case, we have a relation which is simply substitution of this solution into the boundary condition 1. Is it correct for matrices? The answer was no. It was not correct for matrices because for this formula to be correct, we need this equation to be satisfied. The exponent of a sum of matrices should be equal to product of exponent of individual matrices. This is from the very beginning. It looks that it should be so everywhere, every time, but it is very simple to show that it is not the case. And in these papers, Gahov posed the question when this formula works, when this matrix he plus minus z really is a solution of boundary value problem in the matrix case. And the class of matrices was found quite a few years later by Gennady Chebotarev in 1956, and he found this class, and this class is called functionally commutative matrices. Functionally commutative matrices are those, maybe I write it in a big letters because not too much seen there. Functionally commutative matrices are those satisfying such a relation. They are interchanged for every pair of values of variables. This is very strong condition, but it was really the first class of matrix for which factorization can be found explicitly. What is factorization in this case? It is given by this formula. Simply factorization can be given by this formula. Calculation of partial indices is not very hard to have. Not very hard to have, but anyway, it was a first situation when the problem is solved explicitly and completely. But of course, it is very restrictive condition. Chebotarev spent some time to get a special type of matrices of different order in his paper. Order 2, order 3, order 4, and order 5 are described which type of matrices satisfy this condition. It is not because of properties of entries. It is because of structure of matrices. It is because of structure of matrices. It is very a little bit strange because condition looks like condition on entries, but it is not. It is not a condition on entries. It is condition on structure of matrices. And since we pose for us this question about constructive methods, and we know that later on was discovered not too many constructive methods which give us result. Among these methods we can mention that the papers which was discussed by Ilya today. We can mention the papers by Viktor Mikhailovich Dukov and some few other results. Few because not very simple to get constructive factorization. In a sense, we are working with even for very simple classes of function. And today, the rest part of my talk, I will spend to speak about triangular matrices. It looks like triangular matrices, since up to diagonal we have 0. See, it looks like it should be very simple to get solution, but it is not so. There was presented in this paper, there was presented an algorithm which gives us a constructive solution of the problem for 2 by 2 triangular matrices. Idea of this algorithm is very simple. We start with such a matrix which is simply, for simplicity, as usual, we can take them Hoelder continuous, because as a machinery we again use Cauchy type integral. And in this case, we can construct matrix of this type, meaning that each element on diagonal is factorized, and we have this term in this form. It is clear that this matrix satisfies boundary condition. It is clear that this matrix satisfies boundary condition. What next? What's happened next? Next happened, we can calculate.
Sorry for interrupting. Can you go to the previous page?
Yes.
When you have this, the display formula with an integral, you have 5 plus minus, and in the right hand side you don't have pluses.
No. You see, sorry. We start with this matrix. These are elements we factorize. But this shouldn't be simply factorized. We should do something with this element in such a way that we satisfy boundary condition. We take matrix A and we take x minus 1. The factor in this representation for this element, and in denominator x minus 2, the factor, the second factor, the factor in factorization of this. And then we introduce this integral. Because of Sahotski-Plimelli formula, it can be checked that in this case this matrix satisfies boundary condition. This is a simple machinery related to Sahotski-Plimelli formula. What then? Then you remember this is a condition for canonical matrix. Is this matrix canonical or not? We can check just now. It is clear what are the orders of element. The orders of element are on diagonal kappa 1, kappa 2, under the diagonal kappa 2 plus mu, where mu is a order of the function phi minus. You see here, this is of order kappa he2, and this is of order mu. If this relation is satisfied, we are done. So the minimal order are on the diagonal. These are elements has order He1 and He2. The sum of He1 and He2 is equal to the order of the determinant, and we are done. We have we satisfy the first condition of canonical matrix. Since this canonical matrix, then we construct the solution of boundary value problem, and since the relation between boundary value problem and factorization problem, we construct factorization. Done. But if not, the proposal of Chebotarev was to introduce the matrix 1 divided on phi minus in the form of continuous fraction. It was Gennady Chebotarev, the son of Nikolai Chebotarev. Yeah. Okay. Represent in the form of continuous fraction. In fact, from for the beginning, we need only the first element in this. Why continuous fraction? Since phi minus is a minus function, so it is analytic up to infinity. So what we have at infinity simply 0 of certain order. If we divide 1 on phi minus, then we obtain as a main part polynomial. This is a polynomial, this is a polynomial, this is a polynomial, and order of this polynomial is equal to mu. The order of function phi minus, the order of a the order of 0 of a function phi minus at infinity. Then we made some trick already. Chebotarev made this trick. What is bad? The bad thing is that this is too small. The order of this element is too small. Then Chebotarev proposed the following. We have a relation. We have the function He plus satisfy the boundary condition. And we multiply this condition on a matrix 1, 1, 0, minus q in the power gamma 0. Okay. Multiply both sides. Determinant is equal to 0 to 1. That is why we don't change the index of equation or of a problem, but we change the orders of element. After this, we obtain that. In fact, it means that we multiply the certain column on this polynomial and add it to another column. After this, we change the value of elements and again check which order is bigger, which order is smaller, and so on and so far. After a finite number of steps, it was shown that this is really finite because we divide simply the function at infinity, and after finite number of steps, we obtain that the matrix, transform matrix, is already canonical. As soon as we obtain canonical matrix, we are done. As soon as we obtain canonical matrix, we are done. In the title of my talk, I said that we can work with the triangular matrix of arbitrary order. It is really so, and the base for this statement is in the following lemma. In fact, if we have the matrix of this type, the matrix B, then and we know that this matrix A can be factorized, then we can, instead of this matrix, write here diagonal matrix and have only bad row as a lowest row. Here we have already diagonal. This is the base for induction. So if we start with 1 by 1, second 2 by 2, 3 by 3, we can do by using this. And really we realize this to show how it is working. We can say about the matrix of this type. We can start with the matrix of this type. So it means that if we have a matrix of such a type, then we can, by using lemma, we can factorize this block. Then we obtain the matrix of this type, and then we start the same machinery as Chebotarev. Okay, and then we start the same machinery as Chebotarev. It is not, it shouldn't set that it is simple, because if we have a matrix of quite a big order, then the calculations are quite boring. To show this, I show two examples. Maybe since I have only 2 minutes, I show one example. Okay, we can start with this 3 by 3 matrices, and this is the index of this matrix is equal to 2. All is calculated according to lemma. For this block matrix, we know factorization, how to do it. Since it is rational, it is not very hard. Then we calculate these function phi1 and phi2. After that, we obtain these are two matrices which satisfy the boundary condition. But these two matrices are not form canonical situation, because the order of the first column is equal to 1, but the order of the second order is equal to 0. So, and the order of the last column is equal to 0, and so the sum of these orders is 1, but should be 2. What to do? We make a transformation. You see already some boring things, and at last we obtain solution in this form. This is written only matrix He minus, because only He minus give us the answer on the question what is happened with partial indices. And now the partial indices are 1, 0, 1, and so the sum is equal to, and we are done. So this is an example for matrix 3 by 3. Thank you for your attention.
Questions or remarks?
Yeah.
So in the last class of problems you're studying, you have to be able to factorize A in order to proceed.
Yeah, but you see, we can start with matrix 1 by 1, always factorizable.
Yeah.
Next, the matrix 2 by 2, there is a procedure. If we factorize it, then we go to 3 by 3, and so on. But initial point that the matrix considered only triangular.
Other questions?
Yes, I want to make a quick remark in point of clarification for those who were at my talk as well. Things might seem somewhat confusing because Sergei just showed you how to factor any triangular matrix seemingly, and I was talking about the difficulties and even open problems with 2 by 2 triangular matrices. So how do these two things fit together? Here is how. In the class which Sergei is considering, scalar functions are factored.
Yeah.
And if the diagonal entries of a triangular matrix are factorable, the matrix is as well factorable, and that's the procedure which works. What's different in the setting I was considering, it can happen that diagonal entries are not factorable, such entries as the exponents, while the matrix itself, even though it's triangular, is. And that's what makes all the difference.
Yeah, thank you.
I can ask another. So your last example would have rational functions, so you could use pole removal methods.
Yes,
to solve the problem.
yes. We can use many. This is simply illustration. You see, but of course, I would like to say to have the example which is more or less finite. Of course, the methods is working even in the case when phi minus the function which are using here, even if these are function are entire function. So for entire function the procedure is the same. Entire function having certain 0 at infinity, this function can be presented in a infinite continuous fraction, and that is why we can step by step use the machinery.
Okay. Yeah, then I think that there are no more questions at present, and we thank Sergei again.
Thank you.